Hello, everyone. Let's start this session. The last two sessions will be about the oncology use cases and also the identification. And I will be the presenter. I'm Mohamed Shantash. I'm a senior NLP data scientist in healthcare team at Johnson Labs. Welcome. So here is the agenda. After a short introduction, we will go over some case study samples, and then we prepared a use case for you to show how we handle the real-world problems by using the healthcare NLP library. After that, I will explain the solution steps, and then we will go over the code. Johnson Labs is the developer of the healthcare NLP library. Healthcare NLP library sits on the shoulders of the Apache Spark, so it can use the advantages of the distributed system of Apache Spark. So it has been downloaded more than 100 million times according to the PyPy statistics, and this is most widely used NLP library in the enterprise according to the Oriel Media. Also, 59% of the healthcare NLP teams use Johnson Labs, which is really huge number actually. And we have several, let's go over here. We have several peer-reviewed papers in which you can find the accuracy benchmarks, and then the architecture at the behind we use for solving the NLP problems in the real world. There are several oncology use cases. By the way, this session will be will be based on the oncology, but please do not take if your case is not related to the oncology, because I will try to cover how we solve the problems. This is the main topic of this session. Not the oncology. Oncology just for an example here, okay? Just a sample use case we try to provide here. Like there are several oncology use cases handled by the healthcare NLP library. You can find some of them here, which were introduced in the NLP Summit Johnson Labs organized. For example, the Roche, it's a diagnostics and pharmaceutical company, and in their project, they wanted to leverage knowledge graph and NLP to extract key informations from the biomedical text and the databases. And they showed the combination of the knowledge graph and also the NLP for uncovering the new insights in the biomedical field. They use the healthcare NLP library for entity extraction, like medications, genes, like cancer entities, or all the other oncological entities, then checking their relationships between them from the unstructured oncological data. Then they combined the results with the knowledge graph to better analysis and to extract some to help the decision makers, okay, according to the extracted information. In this way, they aim to unlock the provide insights for the experts in developing medication decision or diagnosis. For also the Mount Sinai, if you want to summarize here. By the way, you can check all the use cases on YouTube, Johnson Labs channel, NLP Summit channel actually. So you can just search with these highlights on YouTube. Then you can watch all these use cases. The Mount Sinai team aim to improve patient health and healthcare delivery by using the machine learning to process data from various health records actually, and then they extracted information from the several kind of clinical notes like radiology, pathology, or oncology or psychiatry, nodes using the healthcare NLP library, and they use this information to generate predictive scores and risk assessments for different conditions. Like it can be used for oncology to identify the patients that has the high risk of metastasis. Okay, the platform that they built can achieve 0.4, can achieve 0.84 accuracy in identifying the patients with metastasis. So this can be very useful for identifying the metastasis, the metastasis situation, possibility of the patients actually, which can be prevented beforehand, right? As you can see, just getting the information from the unstructured data by using the healthcare NLP library, you can help people to identify and prevent them from the next diseases, right? Like, as I explained, like for metastasis. Okay, let's start with the use case here. What we will learn in this session, let me cover that topic first. We will learn how we use NER models, how we use assertion status models, relation extraction models, and entity resolution models. All will be explained in this session, and how we leverage those components in real-world problem solving, okay? Let's assume that you're working in an oncology hospital and you want to select the billable ICD-10 codes for the insurance reimbursement. This is really crucial task because some of the ICD-10 codes can be billable while some of them not. And some diagnosis and clinical conditions can be mapped to both of them. Like some diseases can be mapped to billable codes and also the not billable ones. Okay, so choosing them by the people, by human actually, is really open to error prone and susceptible to human error, and really time consuming task, right? You need to hire many medical coders to achieve this, which if in case you have millions of nodes, this is nearly impossible, right? So but we can do that by using the NLP library, healthcare NLP library, with some sort of codes actually that I will explain. There are some keywords here for that can help us to understand the problem and create a plan for solving this problem. Like there's billable ICD-10 CM codes and current diagnosis, and checking them if they are billable or not, right? According to these keywords, we can follow these solution steps. First of all, we need to extract the entities, okay? Entity extraction is the baseline of nearly all cases, actually, all NLP problems, okay? Especially for the healthcare NLP problems. We need to extract the entities with a robust NER pipeline. I will explain how you can create a robust NER pipeline, by the way. After extracting the oncological entities, sometimes we saw that the cancer term, for example, the cancer term can have an ICD-10 code which is not billable, okay, for example, but if there's a body part information in the same text, like lung cancer or brain cancer, so there's a body part information, right? If we use that information also, body part information, with the oncological entity, we can map that to more accurate ICD-10 CM code, right? According to that mapping, we may have the billable code at the end, right? So we need to extract the oncological entities while we also need to extract the body part entities, okay? After getting the oncological entities, we will check the assertion status of those entities because in some cases, in the clinical notes, doctors note that like there is no edema in this patient, right? Or there is no metastasis. Like these kind of terms can be mentioned in the clinical notes, but the NER models just extract the entities, oncological entities. Okay, to checking their negation status, we need to leverage the assertion status models we have, okay, in the library. Also, if it is related to, there are some family history sections in the clinical notes. If the diseases are related, if the terms or the chunks are related to the patient's family, so we need to discard them, right? While calculating the like risk adjustment scores or checking the believable status of those codes, right? So we will use assertion status models. And after that, we will check the relationships between the body part entities and also the oncological entities. If they are in a relationship, we will concat them and map them to the ICD-10-CM codes using the entity resolver models we have, okay? The ICD-10-CM model, we have several resolver models, by the way. For the ICD-10-CM, we have a model that can return the billable information also, okay? Here is the map that we will follow, okay? First of all, we have the clinical text. So since we train our models sentence-wise to have better accuracy, we will split those sentences, we will split those texts into sentences, okay? After splitting the sentences, we will tokenize them and then vectorize them because models cannot understand from the plain text, right? We need a vector. We need to vectorize them. Okay. After the vectorization stage, embedding stage, I mean, then we will send them to the NER model. NER models, we will use more than one NER model in the same pipeline to have in case of one of the NER models miss some entities, the other one can extract, okay? So we will use more than one NER model and then merge their results to get a single chunk at the end in case of overlapping. And then we will send them to the assertion model to check their negation status. After that, we will check the relationships between the between the oncological entities and the body part entities, then send the output to the entity resolver model. It will also return the billable information at the same time. Here are all the oncological models that we have. We have 23 NER models, 7 relation extraction models, and their deep learning versions, and then 8 different assertion status detection models and 2 sentence classification models. We have, as Hasham mentioned, we have model subpage, and then there are several demos. Okay, I will explain. I will show some examples over there, by the way. There are several demos over there, which you can go over and check the model performances on it easily. Like here is the NER model output. Okay, as you can see, we extracted all the oncological entities here, and we can whitelist or blacklist some of them because, as you know, we need, according to our problem, according to our use cases, we may need to drop some entities, right? We don't need some of them, like relative date entity. We don't need this entity for ICD-10-CM, which is not related to the concept, right? So we can discard that. Also the medication entities and the dosage informations, right? So we can whitelist or blacklist the entities according to our use case and then merge their results using the chunk merger annotator that we have. I will show the examples, okay? And then you can understand better there. At the end, we can have a robust NER pipeline that can extract most of the entities. Of course, there will be some false positives since these are, or false negatives, since these are deep learning models, okay? But you can be sure that these are the models that the models that we have are trained with a high accuracy and trained for higher accuracy and with the higher F1 scores, okay? Also, we have biomarker NER models, which can extract the biomarker entities and the biomarker measurements and biomarker results also. Okay. We have another use case in this session especially for the biomarker. Assertion status models are really crucial for these kind of use cases because why? As you can see here, there is no sign of gynecological disorder here, but the NER model extracts gynecological disorder. So we don't have the information of, we don't have the negation status of this by just using the NER, right? So if we extract the entities and then check their relationships and send them to the entity resolution model, we will have some incorrect outputs, right? Because we need to drop this one, for example, okay? Like this is absent. Also, you may want to drop the past ones, right? Because according to our use case, also the family, you can see here, like mother with a lung cancer, we need to discard this according to our use case here. And in our use case, as you may remember, it says that current diagnosis. So we need to filter only the present entities, okay? As I explained for the cancer and the lung cancer example, this is the same for all the other use cases actually, not only for oncology. If we want to have the CPT codes of the procedures in the clinical notes, for example, first of all, we need to extract the entities, right? After extracting the entities that are related to the concept that we are interested in, like CPT, then we need to check the relationships between them to have better accuracy, right? Like CT off term can be extracted as imaging text, and abdomen can be extracted as body part, right? If we send just the CT off term to the CPT model, which will be less accurate than the CT of abdomen, right? As you can see here, like CT, its CPT code is here, okay? This is the concept, and this is the explanation. But if we send the CT of abdomen to the resolver model, we can have better output with different code, right? This directly affects on the accuracy of our pipeline, okay, of our outputs actually. We have, there are several terminologies in medical domain. So like ICD-10, SNOMED, RxNorm, CPT, UMLS, ATC, HBO, ACPCS, etc. We train sentence entity resolver models for each terminologies in healthcare NLP library. And also we try to keep them updated with the latest version of the formal data sets when they release, okay? If any version of the, any new version of the data sets is released for SNOMED, for example, we train our models from scratch and then upload to the model sub to help the customers have the latest version of the models, okay? Also, there are several solutions in healthcare NLP library. And not only, you don't have to just use the relation extraction models and for checking the relationships, for mapping the terms accurately to the their terminology codes. Okay, for if you are working on the entity resolver models, you can also use the sentence chunk embeddings concept that we have. It gets the embeddings of the sentence and embeddings of the term that we extracted. I mean, like this one. And here, it gets the embeddings of CT and then the sentence that CT is in here. Okay, the embeddings of this sentence, whole sentence, and then average that embeddings. In this way, the output of the embeddings is much more context aware. So when we feed that embeddings to the resolver model, we can get the, even though we feed the CT to the resolver model, we can get the code of CT of abdomen term, okay, directly without using the relation extraction model. Like healthcare NLP library is has actually 4 to 6 times fewer errors than the other cloud providers. You may find some benchmarks in our blog posts or our web page actually. Okay, as you can see here, we have better accuracy scores over the all other cloud providers. Also for the ICD-10, 79% success rate we achieved, but the CPT models achieved 26 and 36%. This is the newest one, actually, for the entity resolution. We achieved, when we checked the top 3 results, top 3 results mean entity resolver models and also other cloud providers return except the GPT models. Healthcare NLP library and the Amazon Comprehend can return more than 1 results according to the distances, okay? According to the distances, cosine distances or Euclidean distances in the results. So when we check the top 3 results and top 5 results, healthcare NLP library beats all of them, and which is also less expensive than the other ones, like 5 times cheaper than the other ones. Since we train the models with in-house datasets or some datasets or open source datasets and also the synthetic datasets, they may not perform well on your data, right? In this case, you can train your own model. How we train the models? We have some medical annotators, medical experts, annotation experts. So they annotate the data first. Actually, first they annotate a seed batch, and then when they are agreed on all the terms that they want to annotate, like entities, assertion, and relation extractions, when they agreed on, they start to annotate. Okay. After the annotation process, as a small batch, then we train the model, and then according to the model performances, we pre-annotate the data with the model. In this way, the annotators can see their mistakes and the model performance, and according to that results, they can fix the previous annotations and also annotate the further data sets. Okay, we do this cycle more than 1 time until we have a robust pipeline at the end. Like for example here, let's assume that we have 25,000 documents. First of all, we randomly sample 1,000 documents, and then like some of the data sets, even though they can be larger than the small ones, they may have less entity they may be less useful for annotation, right? Since the annotation process is time consuming, we need to annotate the documents that are rich with the entities, for example, okay? So we can train a binary classification model to check if they are, to classify the sentence, to classify the documents, if they are useful, rich with the entities that we are interested in or not, okay? After the binary classification model, we can run that model on the 2000 documents and then start the annotations according to the results. Like if we have less accurate labels for NER or assertion or relation extraction, then we run the NER model that we trained in the one of the rounds on the other not annotated documents to have the richest documents with that less accurate entity to make it much more better, okay? We annotate those documents and then we train the final model with the to have a robust model, okay? We train the model with the data sets, all we annotated with many times, okay? In the second use case, we will cover like biomarker models, and like if you are working with the oncology researchers and they need to extract the biomarker and biomarker results from the unstructured data and want to create a tabular data with them, but they want to extract just the biomarker and biomarker result entities from the specific sections in the clinical notes. How can we do that? Okay, we will show an example here in this session. As you can see, there are some keywords again, like biomarker and biomarker results that we need to focus on specifically from the sections within oncology notes dedicated to biomarker analysis. Okay. Here are the solution steps for the second use case. Like we will use the sequence classification model first to classify the documents if they are, to classify the sentences if they are related to the biomarker or not. And if they are related to biomarker, then we will extract the entities, biomarker and biomarker result entities from that classified sentences, okay? After that, we will check the relationships between those entities. And if they are in a relationship, we will add them to our tabular format. Okay, that's code. And before going over the code, I want to show the demo page we have, like on our model sub page here. You can search for these tags. According to these tags, if you don't know what you are looking for, actually, like you want to use the entity resolution, okay, and you want to use ICD-10-CM, for example. When you click on that, you may see all the models for ICD-10-CM here, okay, like pre-trained pipelines also, okay. You can also filter the models or pipelines. So when we go over the demo page, we have clinical NLP section, and here is oncology, also radiology or SDOH or risk factors here. So when we click on this, as you can see, all the NER models can be seen here for the oncology and their results with a real-time demo, okay? Then here is a blog post. We not only have the model sub page or demo page, we also have the documentation page that you can find well-documented annotators that we have. If you are struggling with understanding the annotators, how they are working, how you can use them, you can find here. And there are several also like the sample codes here, and Python API, also the Scala APIs are here, okay? You can check the documentation page also. On the other hand, we try to release, we try to publish actually blog posts to explain how we handle the real world use cases to help the people for solving their problems. Okay, like this one, I prepared this one, and this one is you can try to read this for understanding how we for understanding the second use case that we have. Okay, the second use case is the biomarker and biomarker result table, extracting the biomarker and biomarker result table. Okay, so you can read this blog post to understand it better. This is what I mean. This is the specific section in the clinical notes, as you can see. In some clinical notes, there are also some plain text. Okay, but some of the terms here, like MSI, can be mentioned as another term in the plain text. So we need to understand that if it is related to the biomarker or not, right? This is why we will use the sequence classification model first, okay? And here are the biomarker tables, and we will extract all these entities, and we can extract all these entities and create a tabular data from the unstructured data, okay? Also, another oncological use case explanation here, like cancer types. For cancer types, you can read this blog post here, and we have cancer types model, which can detect the cancer types, and then you can extract all these information from the unstructured data, as you can see, okay? And another one is for checking the response to cancer treatment. As you may understand from the highlight, this is really crucial task. So to checking the patient's responses for the cancer treatments, we can try to extract some information to help the healthcare providers for this. You can find an example in this blog post. Okay, when we go over the notebook, you can see the highlights here. There are two different use cases. Like the first one is checking the billable ICD, mapping the clinical terms to the billable ICD-10-CM codes, and then the biomarker and biomarker result table generation. Okay, so let's go over here. These are the solution steps. First, we will extract the entities, then check their assertion status, and then check the relationships between the oncological and body parts, and concat them if they in a relationship. If they are not in a relationship, we will just send the oncological terms to the entity resolver model. Okay. We upload the libraries and we upload our license and download the install the libraries that we need. After that, we start a Spark session, and you can list all the oncological models that we have, as we did here, like this one. You can see here. Also, this table can help you to choose which models you can pick for specific labels. Like for the age entity, you can use in your oncology model, also in your oncology demographics model, right? And this table can help you to choose in your models according to the labels that you need to use. Yes, we used and sample oncological nodes, MT sample nodes, actually, which is open source. And this dataset is used here for our use case. We have 10 different oncological nodes here, as you can see. And here is how the data looks like. This is one of the sample nodes. And there are some sections here, and past medical histories and family history, as you we need to consider this one, right? We need to discard that section. And then first we will extract the entities, right? since we are working on the oncology test, we need to pick the best NER models first. How can we pick the best NER models? How can we know that which model is better performing on our data? We have NER profiling oncology pre-trained pipeline. Okay, this can be loaded just one line of code, and you pick some sample nodes, okay, sample clinical nodes, and run on it. When you run on this pipeline returns all the results from all the oncology models that we have. We have also NER profiling clinical model, which contains more than 80 NER models inside. Okay, for the other tasks, you can check this. It can return for a sample node all the 80 different NER model results with a one line of code. Okay, like here, 33 NER models we have, and this is the output. So how you can pick that, how you can know that which is better for your use case, you can just check this notebook, check this output, okay, one by one, and see which model is performing better on your data, okay, according to your needs. Like, for example, if you are working in an anatomical oncology and anatomical test, you may don't want to use the unspecific pathology model, right? This is not related to your test, but sometimes some of the models may have some common NER levels, as we showed here, even though their titles are not related to each other. Okay, you can use any of them. If you are working in an oncology task, you don't have to use only the oncology models. You can use any models in Spark in healthcare NLP library. Okay, you can add any of them, and then, like for example here, we use document assembler, sentence detector, and tokenizer here. It gets the text and splits sentences, then tokenizes, and we vectorize all these tokens with the embeddings model. And then we need to consider a crucial point here. The embeddings model should be compatible with the NER model or the assertion model or the relation extraction model you are using in the pipeline. You can use more than one embeddings model, but which means you will tokenize all the tokens, you will vectorize all the tokens 2 times or 3 times, how many embeddings model that you use according to. Okay, so we used NER oncology model here. As you can see, we whitelisted the labels that we are interested in, right? There are several labels in this model. So we just want to use just these labels, okay? And we can also replace the labels with any term that we want to see. Like, I don't want to see site bone in the output. I want to see it as an anatomical site, okay? To make it generalized, which also can help us to create the relationships between the entities, relation pairs, okay? I will explain in a minute. So this model is used for the anatomical side also, okay? And this model is not oncology model, NER-GSM model, but it has 80 different models, the 80 different entities inside it can label, okay? 80 different labels. So we just wanted to use it here. Even though it is not an oncological model, we can use it, right? If this is performing well on our data, we can use it, and we need this. And if we need the label, one of the label for this model, okay? Like we wanted to use oncology label, internal organelle component, and external organelle component, which are body sites, right? Anatomical sites. So we renamed them as an anatomical site. We don't have to, as I explained. And now we merge them. While merging the entities, the outputs of the NER models, like chunks here, we use chunk merger to get a single chunk at the end, okay? In case of overlapping, we can handle these overlapping issues by using the chunk merger approach. Also, if you want to see all the results, even though they are overlapping, there are some parameters for this, okay? Like set merge overlapping as false. When you set it, it returns single chunk. But if it is true, it returns all the overlapping results, okay? Also, you can prioritize these models. Like, for example, if you don't like the output of the in your oncology chunk, and like for example, the NER oncology anatomy model performing better than the oncology chunk oncology model, you can just replace this one to the left side, or set some parameters for prioritization of the outputs, okay, which is really flexible, and it helps us to manipulate the pipeline, manipulate the results at the end, okay? Here also, another component that we have, you can filter the chunks that you want to see at in your results, okay? For example, like this term was labeled as a false positive, okay? You can just blacklist it, okay? This is rule-based, just write it inside, okay? You can also filter the entities according to their labels. This is also doable. We create the pipeline and then transform it with our data, where it is. Before going over there, like the NER oncology labels, this is the NER oncology output, which is one of our states here, okay? If you would like to see the which labels these models have, NER models, you can just check the labels that this model have by using the get classes method, okay? NER oncology dot get classes method returns all the labels that this model have, okay? Since this is an NER model, it has B and I tagged labels and also O labels, so that after making some processes here, we can have these labels. These are the labels that this model can return, can extract, okay? So according to this output, you can whitelist or blacklist the terms that you are interested in, okay? After transforming the data, yes, just give me a second. Yes, after transforming the data with our pipeline, and then we have this output, okay? All the components that we used here, all the components that we have here returns as a new column in our data set, okay? You can see here all NER oncology and NER oncology chunk, as you can see, like NER oncology and NER oncology chunk. Then we can check the outputs by visualizing, okay? We have NER visualizer, and you can easily check the performance of the pipeline that you created, if it is good or not, by visualizing on a sample node, short sample node, then decide which labels are performing good, on which labels the model performing good or not, okay? Like this model returns Like this is the term that I want to remove from our results, like hand. So as you may remember, I just filtered it, and here it is not exist in my final output, okay, NER chunk. In our pipeline, after the merging the entities, we have the output NER chunk, okay, after the filter. So this is our final output. So when I check it, the term that I filtered is not over there, okay? This is the final output, and you can see also the other model performances, okay? We write the results after transforming the data. We write the results as Parquet file. If you would like to have the advantage, if you would like to leverage the advantage of the distributed system, we suggest you to read the data from a Delta table or a Parquet file, which supports the distributed system advantage of the Spark. Okay. In this way, if you read the data from CSV file, just a single node reads this, and all the process goes on a single node. To leverage the advantage of the distributed system, if you read the data from a Parquet file, Spark Parquet file, then it distributes the data to the all nodes we have and cores, then it processes simultaneously, okay? We write the output as a Parquet file here. This also helps us to, we can create the pipeline. We can create a single pipeline that can do all these states at the same time. But this is too risky if you are working with a large amount of data. In case of any issue happens, you need, if the process is broken, right, you will lose all the results, all the processed results with the waiting ones, right? Instead of having this issue, we can split the pipeline into different sections and then save the results in each step as a Parquet or Delta table. By dropping, you can also drop the columns that are useless in the previous for the next stage. Okay, and this will help you to save them much more faster. Okay, the assertion status. We can create another chunk merger for the assertion status, or just use the chunk filter. But at this time, we just filtered the blacklist. We just filtered the entities with their labels. Okay, we set filter entity, and the blacklist is the label, because we don't want to check the assertion status of the body parts, right? It cannot be passed or absent, right? So this doesn't help, and we don't need it. So we just want to check the negation status of the oncological entities, okay? So we use the assertion model here and then assertion filter here. Why we use the assertion filter? Because according to our problem, it says that we need to current diagnosis, right? So we need to extract only the present entities from the clinical node. And then you can see here all the present oncological entities, right? These are the entities, and we wrote the results as pandas CSV. After this stage, we can use the pandas. Okay, we can also go over with the, we can also go ahead with the Spark, but here we wanted to show how you can use the pandas with our components, okay, with Spark NLP. But right now, we need to also check the relationships between the body part and the oncological entities by using the relation extraction. As you can see here, like the cancer, its ICD-10 code is C80, but the lung cancer has completely different level, right? Different code, ICD-10 code, which can be billable, and this one may be not billable. Okay, to mapping the ICD-10 codes more accurately, we need to check the relationships between them, between the body part and the oncological labels. Okay, here we create the relation pairs. Since we replaced all the body side or internal external body components with the anatomical side, we just create this. Okay, these pairs. According to the pairs, and you can see the results here. Let me find one. Yeah, like here, temporal margins of the lesion. If we wouldn't check the relationships between them, we just get the ICD-10 code of lesion only. But right now, we can check the temporal margin lesion. When we concat them, merge them, and feed that to the ICD-10 resolver model, then we can have more accurate results, right? But yeah, here are the outputs. We followed some processes here. You can read the notebook and check that. According to the assertion, also, we need to drop the entities if they are not present, right? Even though we merge even though we merge them with the body part entities, anatomical sites, we need to drop them, right? Since they are not current. So here is the final output that we have. As you can see, we like ductal carcinoma of the breast, for example. We merged them, right? After that, we will get the ICD-10 codes using the entity resolver model. Here, the entity resolver models can work slowly because we use BERT embeddings in the entity resolver models. This takes too much time, okay, while getting the embeddings of the terms. So there are several steps for making it faster, okay. We also have a vector DB entity resolver API right now, which is much more faster, and also it is sparkless, okay. If you have a list of chunks and want to map them to their corresponding SNOMED codes, allowing codes, or RxNorm codes, you can use that API to get faster results. After getting the entities as a list of chunks, okay, we lowercase them, okay, and because it doesn't affect the performance of the resolver model, if we query the uppercase or lowercase, it doesn't matter. So we lowercase all of them and drop the duplicates. In this way, as you can see, the count of the entities drop nearly half, right? If we wouldn't do this, we need to get the embeddings of the same terms again and again, okay? And the results from the resolver model. This will be much more time consuming, and also it needs much more RAM, right? Resources will not be used effectively if we wouldn't do this, okay? But we drop the duplicates. We just have 33 terms right now to get the embeddings and also the ICD-10 codes, okay? When we check this code, this model on our model subpage, pardon, couldn't copy it. Yeah. You can see the descriptions and all the details of this model in the model cards. Yeah, here are the descriptions. So this model can also return the billable status, HCC status, and HCC score of the ICD-10 codes in the all K AUX labels column in metadata. Okay, I will show what I mean. Like when we get the results, it can return these informations. Okay, like when we check here, you can see OK AUX label in the metadata of the output, and here are the billable information. The first digit is billable information. The second one is HCC status, if this is HCC, and this is the HCC score, okay? And this one also is billable. This is not, okay? So you can find the details in the model cards, the explanations, and also the references that we trained the model in which version of datasets, okay? So we get the resolver model outputs and then merge it with the R59 chunks, okay, to keep the original one if you would like to. And you can merge them. But as you can see, if we wouldn't drop the duplicates, we need to get the embeddings of this term 3 times and send the resolver model 3 times, okay? But when we drop it, we kept the memory and also time from this risk, okay? And when we process some after processing, when we do over the billable column here, we can have not billable and billable columns with ICD-10 codes, and this is the result, as you can see. Okay, these are the billable codes. So we achieved this. Okay, let's give a 10 minutes break. Okay, and then see it in the second use case, and then go over the de-identification. See you in 10 minutes.